This is the third lecture related to the basic foundational concept of linear systems, which is what Chapter 3 is all about. In previous lectures, we looked at specific linear systems and looked at solving those systems using the idea of straight line solutions, eigenvalues, and eigenvectors. And I gave you a quick overview of a particular example showing how to solve, how to find the general solution for that particular example. In this lecture, I'd like to emphasize something else. What have we emphasized in this course? What do I try to emphasize? I've tried to emphasize conceptual understanding. Do you understand the big ideas, how they're related? Do you understand how the graphical interpretation of solutions and the phase plane relate to the differential equation? We've emphasized applications, at least the book does and my Mathematica notebooks do. The kinds of applications that you've looked at so far involve, for example, predator-prey models, mixing problems, a little bit with masses on springs. And we also emphasize, you might say, problem solving. Something we de-emphasize is mathematical proof. However, as you've probably seen from some videos in Chapter 1, I don't completely eliminate it from the course completely. This is going to be one of the videos where we do try to spend some time focusing on how would you go about proving things to really get a good, solid understanding of what's going on. I've titled the lecture, Overview of Linear Systems of Differential Equations, and you can see I've made it as a PowerPoint presentation here. So in this lecture, I'm going to overview the eigenvalue, eigenvector method and talk some about the theory that can be used to justify it. And this is important. I do want you to know this material. I want you to understand it and be able to deal with questions related to this kind of thing on the exams. What I like to do in teaching theory like this is I like to sort of work backwards. I kind of like to deconstruct the theory. When you read math textbooks, quite often you see just the finished product, the finished, polished product that, well, is very pretty, and mathematicians enjoy looking at that finished product a lot, but it doesn't really give you a whole lot of insight into what kind of thinking went into that finished product. It sort of feels like things are being pulled out of a hat. Why did the author think to do that or this? So I want to deconstruct that process by working backwards. Thinking about, first of all, what is our method? Let's outline that. The method for solving an arbitrary linear differential equation, system of differential equations, and well, I should have tested this ahead of time. You can't quite see the dy dt there, but that is what's there. dy dt equals a times y. And I'm going to talk in the general case where A is an n by n matrix and y is an n-dimensional vector. Though in almost every problem that you consider in the textbook, you are working with two-dimensional systems, a 2 by 2 matrix A and a two-dimensional vector y. But these ideas carry over to higher dimensions, and so we might as well talk about them in higher dimensions. Though when you are trying to spend the time to understand it, you probably will want to think two-dimensionally. So what was the method? For solving that system, for finding the general solution, the first step was to find the eigenvalues of A. That's the first step. Once you find the eigenvalues, then you want to find the eigenvectors. I'm only going to be considering one kind of case that you encounter near the beginning of Chapter 3. Once you get into 3.4 and section 3.5, then you get to more complicated situations. I'm going to assume that the eigenvalues that I get from A are real and distinct. And based on that assumption, we'll get real eigenvectors that happen to be what are called linearly independent. Linear independence is actually kind of a tricky concept. At least once you get past 2 dimensions. You'll want to think 2-dimensionally. For 2 dimensions, if you've got 2 fixed vectors, they will be linearly independent. 2 fixed non-zero vectors will be linearly independent if and only if they're not parallel to each other. They don't point along the same line if you put them with the base at the same point. When you go to higher dimensions, the idea of linear independence becomes more complicated. But intuitively, if we're thinking 3 dimensions, say, a set of 3 vectors in 3 dimensions will be linearly independent, basically if and only if they don't lie in the same plane. A set of 3 non-zero vectors will be linearly independent if and only if they don't lie in the same plane when we put their base at the same point. And there are higher dimensional analogs of that. I don't want to get into it. Think 2-dimensionally. Think of the fact that you've got 2 non-zero vectors that are not parallel to each other. Complex eigenvalues and repeated eigenvalues, where the characteristic polynomial has a factor, for example, of say lambda minus 3 quantity squared or quantity cubed. Those cases will be dealt with later. That's hard. So I'm always going to assume in this particular lecture from now on that the eigenvalues are real and distinct. What's the next step? Well, for each eigenvalue-eigenvector combination, lambda and v, form this function right here. This is a function of t. Think of the lambda as fixed and think of the v as fixed. It's a vector-valued function. For the real input t, you get a vector out, the scalar e to the lambda t times the vector v. That can also be thought of as a parametric curve. As t varies, it's going to describe a curve in the plane if v is 2-dimensional or 3-dimensional space if v is 3-dimensional. And you can go on in 4-dimensional space if v is 4-dimensional. Then, the final step to constructing the general solution is to take an arbitrary linear combination of all these vector-valued functions. And that would be the general solution. A linear combination means you're adding those vectors together, well, with the condition that you're multiplying them by scalars too. So you will typically write your general solution in this form. I'll put it up on the board here. Y of t will equal an arbitrary constant, call it c1, times e to the lambda 1 t times the vector v1, plus c2 e to the lambda 2t times the vector v2. If it were a 2-dimensional case, you'd stop right there, but if we're doing the general case of n dimensions, we have a bunch of intermediate terms, and then the last term will be a constant cn times e to the lambda n times t times the vector vn. And that will be your general solution, which you can use to solve any initial value problem. So let's deconstruct this process. Why does it work? Issue number 1. Why in the world seek eigenvalue-eigenvector combinations? The reason goes back to the vector field or the corresponding direction field and making observations. Sometimes you can think of math observationally. You can notice patterns, and based on those patterns you can try to come up with rigorous math. You can use the computer to explore vector fields, planar vector fields in this case, and quite often you will see, for linear vector fields at least, that the vectors seem to point straight away from the origin along certain lines, or at least pretty close to straight away from the origin. It might be a little deceiving based on which particular vectors happen to get plotted. And sometimes they point straight toward the origin, in this case along this line. So for example, for this point right here, at the tip of the black arrow is its position vector. Call that point V. The black vector would correspond to V. The blue vector that you see there is A times V. That's the output of the vector field that's pointing straight away from the origin when you put its base at that point, V. We notice that this happens, and because of the fact that we know that solution curves follow the vector field, this leads us to think that there could be solutions to these linear systems that lie along straight lines. And straight lines are good in math. Straight lines are simple compared to curves. That leads us to thinking that perhaps we can actually find formulas for those straight line solutions. The idea that we can find straight line solutions is based on this observation that for many linear vector fields, there seem to be lines along which the vectors point straight toward or straight away from the origin. Well, just because those are straight line solutions, they lie on straight lines, doesn't necessarily mean the corresponding function that parameterizes that straight line will necessarily be a simple function. However, from our experience with scalar differential equations, we know that quite often exponentials play a role. And that leads us to guessing at what the solution curves might look like. And that leads us to guessing something like that. Once we've found the scalar lambda and once we've found the eigenvector v. Coming back to this picture, the v in that formula is really the black arrow. That's the eigenvector. There are lots of eigenvectors. Any non-zero vector along that line will be an eigenvector. Lambda, the eigenvalue, is going to be, in essence, the scale factor. How much longer is the blue vector than the black vector? Looks like maybe it's about twice as long. Lambda, in this case, could be very close to 2. But let's review how to find eigenvalues and eigenvectors. How are they defined algebraically? For a given non-zero position vector v, the output of a linear vector field A times v will be parallel to v, or will be the zero vector, if and only if A times v is a scalar multiple of v itself. A times v is some number lambda times v. Technically, lambda could be 0. Lambda could be 0. Then the output of the vector field would not be parallel to v. The output of the vector field at v would just be the zero vector. It would just be a dot. And in fact, you'd have infinitely many equilibrium points along that line that v lies along through the origin if lambda ends up being 0. But that doesn't usually happen, though when it does happen, it's important. So effectively, you can imagine lambda to be a non-zero scalar here. Lambda could be negative, though. That would mean the vector field is pointing in the opposite direction of v. If we let I be the appropriate identity matrix, if v is n-dimensional and A is n by n, then I will have to be an n by n matrix, n rows and n columns. The arbitrary n by n identity matrix is usually written with this kind of picture. We have to use dot, dot, dots because we're not specifying exactly what n is. Well, that would be a 1 here. You'd see pictures like this to specify an arbitrary n by n identity matrix. You've got 1s along the main diagonal from upper left to lower right, and 0s everywhere else. You multiply that times an arbitrary n-dimensional vector, and you will get the vector back out. So we think of v as I times v. Then take this equation, AV equals lambda v. Rewrite it to look like this. Subtract lambda v from both sides of the equation. And then replace v with I times v. And factor out the v on the right-hand side. And that'll lead you to this equation. The matrix A minus lambda I times v equals the 0 vector. We're looking for non-zero solutions to that, so we're looking for values of lambda that make that matrix singular, non-invertible. We're looking for values of lambda that make that equation have non-trivial solutions. And the condition we discussed for when that has non-trivial solutions is when the determinant of that matrix is equal to 0. So we're seeking values of lambda that make that true. This expression here ends up being a polynomial in the unknown lambda that you can solve for lambda. In the n-dimensional case, that'll be an nth degree polynomial. In the two-dimensional case that we usually consider, it's a quadratic that you can solve with the quadratic formula, or if you're lucky, by factoring. The determinant formula in 2 dimensions is much simpler than higher dimensions. You have say a 6 by 6 determinant. Well, good luck. It'll take you probably an hour or so to find the determinant of a minus lambda I. That's something you can look into on your own if that comment made you interested. Probably not. Why is e to the lambda t times v a solution? That's another issue. Why is it a solution of this differential equation? dy dt equals a times y. That's actually pretty easy to verify if you really understand what you're doing. It follows easily from the chain rule and from the definition of eigenvalues and eigenvectors. Now you have to believe that the chain rule works for vector valued functions, but that's just an easy consequence of the fact that we differentiate a vector valued function component by component. Differentiate each component individually. So the chain rule definitely works. And here would be the verification right here. As usual, when we try to verify that something is a solution to a differential equation, we plug that function into the left-hand side, simplify, and plug it into the right-hand side, simplify, and see whether we get the same function out at the end. This is an abstract kind of thing here. I'm not specifying what A is, and therefore we don't know what V and lambda are, but based on abstract principles, it's easy to verify. This is the chain rule right here. I guess it's not super abstract because we do have a particular kind of function, an exponential. Based on the chain rule, you're just going to get an extra factor of lambda in front. That's the derivative of lambda times t. And so that's what the left-hand side simplifies to. What about the right-hand side? It simplifies to the same thing, though the chain of reasoning is a little bit more involved. Technically speaking, we replace y with e to the lambda t times v. Technically speaking, the first thing we need to do is use a kind of, you might call it a commutative property, I suppose. I'm not sure if that would be its official name. You're, in a sense, factoring out an e to the lambda t. You can factor the scalar out. When you have a matrix times a vector where the vector is represented as a scalar times another vector, the scalar can be factored out front. That's some algebra that can be easily verified. Now use the fact that v is assumed to be an eigenvector for some eigenvalue lambda, so therefore we can replace a times v with lambda times v. And then once again use a multiplicative commutative property to rearrange this, switch around the lambda and the e to the lambda t to get this, which matches this up here. So that's some algebra here, and the definition of eigenvalues and eigenvectors for that equality right there. The left and right hand sides match, and so we have verified why e to the lambda t times v is a solution. Two more issues. Issue number 4. Why is a linear combination of solutions still a solution? This is an issue that you've read about before, even in Chapter 1. It's the linearity principle. This follows from the linearity principle for linear systems. In its most general form, it says that if you've got n functions, y1 of t, y2 of t, up through yn of t, that are solutions of this n-dimensional linear differential equation, dy dt equals ay, and if you've got n constants, c1 through cn, then this arbitrary linear combination of those functions, these constants are arbitrary, is also a solution of this equation. And once again, to prove this, it's the left-hand side, right-hand side game. Plug the function in on both sides and see what happens. And the truthfulness of this is going to follow from other linearity properties. Linearity of the derivative operator. When you differentiate a linear combination, you get the corresponding linear combination of the derivatives of each function. The coefficients, the c1 through cn, still stay the same. That's something that you have used since Calculus 1, that you can differentiate sums of functions piece by piece, and you can factor constants out, carry them along for the ride. It also works with matrix multiplication. A times this vector, this arbitrary linear combination, is a linear combination of A times the individual vectors in it. Now, I didn't put the of t's in these y's, but I could have. You should realize that quite often in differential equations we're a little sloppy and we don't always put the independent variable in for the function, so you have to keep track of what's the function and what's not. Those facts can be verified when you know some calculus. In the definition of the derivative, that depends on linearity properties of limits. The definition of the derivative and linearity properties of limits is what allows you to say this first equation is true. For the definition of the derivative, if we're talking about a one-dimensional function, f prime of x is a limit of f of x plus h minus f of x divided by h as h goes to 0. And limits have linearity properties. The limit of a sum is the sum of the limits. And based on those facts, you can use them to derive this property, the linearity of the derivative. The matrix multiplication is just based on the definition of what it means to multiply a matrix times a vector. Finally, I just want to mention that the linearity properties of limits are based on the rigorous definition of a limit, something called the epsilon delta definition. If you've heard of that before, you're probably saying, oh, yuck. Well, maybe there's a few of you that enjoyed that. If you haven't heard of it before, well, go look it up. Maybe you won't like it. Maybe you will. It's something that math majors have to deal with when they get to a course called real analysis. I personally enjoy it a lot. I didn't necessarily at first, but after time goes by and you study it long enough, it rubs off on you and you can enjoy the epsilon delta definition of the limit. Final issue is, how do we know that we have the general solution? Once we write our arbitrary linear combination of our linearly independent solutions, how do we know that it's the general solution? Here's the issue. If we've got n linearly independent solutions, and then you've got an arbitrary solution, y of t, to some given initial value problem, how do you know that you can write y of t in this way? In essence, how do you know you can use these linear combinations to solve any initial value problem that you want for some choice of constants c1 through cn? I'm not going to go through the details of how we know this, but I will say this. It's a consequence of the uniqueness theorem, for one thing, along with the fact that if we are given a set of n linearly independent vectors in n-dimensional space, then any given vector in n-dimensional space can be written as a solution, as a linear combination of those given vectors at the start. I guess I use the word given a little bit too much here. If you're given a fixed vector, let's say not parallel to any of these n vectors that you're given also, if all those other n vectors are linearly independent, you're going to be able to write that other vector as a linear combination of those n. Okay? That's possible to show. In a class called linear algebra, they would do that. So we've sort of deconstructed the process to try to justify that this method really does give us what we want. It really gives us the general solution. All these pieces fit together to really to prove that. Of course, when you're thinking about proofs, quite often students have difficulty with proofs. Not only are they hard to come up with in the first place, but even when you're done, quite often you're not really sure if you're done. You're not really sure if you've done it right, and so you want feedback from your teachers or your colleagues, if you're a professional, about whether something is right or not. A couple of videos from old movies that illustrate this with arithmetic. These are pretty funny. Abbott and Costello, of course, are very funny guys, but I actually thought that this particular one from a Ma and Pa Kettle movie from either the late 40s or early 50s was a little funnier, and we'll end this video by watching that. There it is. So we'll want to zoom in on this here and get the volume loud enough. You may need to turn up the volume on your computer. You can sit back and enjoy.
About the percentage. I figure 75% to you, Mama, and 25% divided between the 5 of us. Giza, Crowbar, myself, Tom, and the baby. That makes 5% for each one.
Billy, you're cheating yourself. If there's 25% divided among the 5 of you, that's 14% apiece.
Oh, no, listen, Pop. I wouldn't cheat you. You know I wouldn't. Now, look here. I'll show you. Let me rub this out here. And, now, 25 divided by 5 is 5. You see, the 5 won't go into 2, will it?
He's
no.
trying, hopefully you can see that.
25,
5, 25, and then a 5.
Now, I'm pretty good mathematician. Now, 5 into 25, 5 won't go into 2.
No.
But 5 goes into 5 once. Now, we didn't use the 2 before, so it's right down here. Now, 5 into 20 goes 4 times. There you are. 5 into 25, 14.
No, look, Bob. Now, let me prove it to you now by multiplication. 5 times 5. 5 times 5 is 25.
I'm surprised you're learning.
Huh?
I'm surprised that you're learning. Now I'll show you. 5 times 14 is 25. 5 times 4 is 20. 5 times 1 is 5. 20 is 5. That's it.
No, look, Mom. Look, you're wrong there because I'll prove it to you. If we put down 5 14s here. 14. There. Now I'll prove to you by addition that 5 14s is not 25. 4, 8, 12, 16, 20,
21, 22, 23, 24, 25. There you are. Better brush up, Billy. I don't want to see you boys cheating.
Well, if you couldn't hear or see that very well, the place you can go to find it is www.math.harvard.edu, then slash, and then one of those little curly symbols, the squiggle, KNILL/math movies. And you can hopefully hear and see it better there.